leave it there because 1.5 is very short. So I want you to give it a shot, because the only new piece of information in 1.5 is the slope. If you find a line and you know its slope, find the slope that's find the slope of a line that's perpendicular, find the slope of the line that's parallel. So take a look at 1.5. You've got the blank notes up, and there are videos in there as well. So give it a look over. Definitely finish 1.3 tonight, 1.4 by next Tuesday, and then we'll see how 1.5 goes next week. Do all you can in there, and if it's too much left over, we'll extend it to Thursday. All right. So let me show you really quickly what this is after. Ignore this top for a second. We'll come back and deal with that next time. If I have a line and I want to find another line that is parallel to it, those two lines have to have the same slope. So if slope 1 and slope 2 represent the slopes of two non-vertical parallel lines, then the slope of m sub 1 is equal to m sub 2. If the slopes of two non-vertical perpendicular lines, then m sub 1 is equal to, this is the opposite, oh my goodness, that's way too thick. This is the opposite reciprocal, right, of M2. Okay, and what does it do? It goes from, so it's M2 is, if M2 is just sitting there, its opposite reciprocal is, it's in the numerator, move it to the denominator, and then change the sign out front. So that's why you don't hear me just say the reciprocal is the opposite reciprocal. If M2 is positive, its opposite reciprocal is negative, and everything changes places. So if I had 3/4, if M is 3/4, and I want to find the slope of a perpendicular line, that little upside down T means perpendicular. That means I would have what's in the numerator goes to the denominator, what's in the denominator goes to the numerator, and the sign changes. We've got -1/2. A line that is perpendicular to this would look like what? So it's 2 over -1, but then I have to put the negative out front because it's opposite reciprocal. 2 divided by -1 is -2, and -2 is 2. Okay? So take that with you, see what you can do, get all of 1.3, 1.4 done, see what you can do in 1.5, and then I'll see you all on Tuesday, and we'll finish up 1.5 and hopefully have a better calendar ready. All right? Okay, if you got any questions, stick around. If not, go be safe, and I'll see you all next week. Okay, then, did I get it? I've got some definitions at the bottom here. We have lines. Lines are going to be lines can be one of three things. If I have a pair of lines or a set of lines, really just a pair, just two. If I have two lines, they're going to have one of three relationships. They're either going to be parallel, perpendicular, or neither. Typically call that a skew. It means they intersect. They just don't intersect at a special 90-degree angle. So parallel means they never touch. Perpendicular means they intersect, but they intersect at a 90-degree angle. So when we draw the lines, you end up with a T. Okay, and that's where you'll see some of the notation come into play because the word parallel is so long. You'll see us shorten that as just the two lines from the two L's. And then perpendicular is quite long. So perpendicular will be represented by an upside down T. Okay. And then askew doesn't have a symbol because most lines are askew. All right. So if I have two lines that are parallel, what that means is their slopes must be the same, right? Because if they're parallel, it means they go on forever without touching. They never touch, never cross, never do anything, right? So they've got to be continuing at the same rate forever. So the question is, for each linear equation or linear function, find the slope of the line that's parallel to the line that's perpendicular to the line. So just the slope, don't overdo the question here. So the first one we talked about before, f of x is equal to x plus 3.5. Remember, f of x is fancy y, so if it helps you, which is y is equal to x plus 3.5. That looks like my slope intercept form. So what is the slope of the line? Well, the x doesn't have a coefficient in front, so it's an understood 1. Okay. So the slope for a parallel line is going to be the same, and the slope for a perpendicular line is going to be the opposite reciprocal. Trouble is the value of this is 1. 1 over 1, when I find the reciprocal, it's the exact same thing. So it doesn't really do me any good. So what does a perpendicular look like here? Well, 1 over 1, and it gets a negative. 1 divided by 1 is 1, so my slope is negative 1. So if I have a line that has a slope of 1, if a line is perpendicular to that, it means it must have a slope of negative 1. Okay, what does that mean? It means that, let me show you an example here. And just write just a real quick, y is equal to x, y is equal to negative x. There's your perpendicular. Okay. You see how where they cross one another, they split into with 90-degree angles on both sides? That's what it looks like. So a slope of 1 is the purple line, a slope of negative 1 is the black line. All right. Now, for the next one, I have an equation, and I'm asked to find the slope of the line that is parallel and perpendicular. So here's the problem. I can't tell you the slope of the line parallel and perpendicular to 4x plus 3 halves y minus 6 equals 2 because I don't know the slope of that line, right? I need to know the slope of the line so that I can find the slope that's parallel and the slope that's perpendicular. These are all part of our answer. All right, so how am I going to find the slope of this line? The best way to do it, you can do it two ways. You can either use the slope formula and find it, or you can get your equation in slope-intercept form. And whenever you're given an equation, it's usually easier to get it in slope-intercept form. So let's start out with what we have, 4x plus 3 halves y minus 6 equals 2. I'm going to get rid of fractions first. So the only fraction in here is that 2 in the denominator. So I'm going to multiply both sides by 2 to get rid of it. 2 times 4x is 8x. 3 halves y times 2 is 3y. Negative 6 times 2 is negative 12. And 2 times 2 is 4. Now solve for y. So everything with a y stays, everything without goes. So add 12 to both sides. And I've got 8x plus 3y is equal to 4 plus 12 is 16. That's annoying. Okay, we're getting there. It's a slow process. Everything with a y has to go to the other side. Everything without a y goes to the other side. All right, so subtract 8x from both sides. And now I'm looking at 3y is equal to negative 8x plus 16. Y is almost by itself. It's currently multiplied by 3. I need that 3 to go away. So I'm going to divide by 3. If I do it to one term, I have to do it to all of them. And I end up with y is equal to negative 8 thirds x plus 16 thirds. All right, which means the slope is negative 8 thirds. So the parallel slope is negative 8 thirds, and a perpendicular slope is flip and change, positive 3/8. The toughest part about this question is keeping track of the work you've done and making sure you're always moving in the direction of the solution. Okay? All of the work to get us so that we can find the slope, so that we can then find the slope of the parallel and perpendicular lines, all of that work is old stuff. We've done that before. The new stuff is just what's in the box. Parallel lines must have the same slope. Perpendicular lines must have opposite reciprocals. Okay, so that's enough of me talking. That's our answer for the second one. You take the last two, come up with what you got, and then tell me your answers. All right. Sorry about that. I had to step away. But we should have been able to tackle 2x minus y is equal to 18. That line has a slope of 2, which means the parallel slope is 2 and the perpendicular slope is -1/2. Remember, 2 is 2 over 1. So when I take the reciprocal, it flips to 1 over 2. We just don't typically write that part out. We just say, if I have 2, the reciprocal is 1/2. But remember, any whole number, any integer can be rewritten as itself over 1, and it's still equal. Okay. Last one, f of x is equal to 1/2. That is, again, fancy. That is the Grey Poupon, which, gosh, do you even get the Grey Poupon joke? Or has that just gone? Has that just left the world? No? Okay, thank you, because my references, turns out when you're 13 years in, your references are just not what they used to be. So f of x, there's an old commercial where a limousine pulls up beside another limousine, and he said, would you happen to have any Grey Poupon, which is just fancy mustard, instead of saying, do you have any mustard? So that's the commercial. Anyway, f of x is fancy y, so this is y is equal to 1/2. And what am I supposed to do with that? Okay, well, what's the slope of this line? Slope of this line, well, it's y equals 1/2. That is a special kind of line. Okay. What's missing here? X is. When x is missing, and you just have y, you'll end up solving for y. What this is a horizontal line. With a slope of 0. All right, and why is that? Because x is missing. So you can expand this to think of it as y is equal to 0x plus 1/2. 0 times x just goes away. So a slope of 0. Okay? Any parallel line is also going to have a slope of 0, but the perpendicular line is going to cause some problems. 0 is fine. 0 over 1 is fine, but when I flip this, I cause division by 0. All right, whenever you see division by 0, you stop and run the other way. That's undefined. So that means the slope of any line that is perpendicular to y is equal to 1/2 or f of x equal to 1/2 must have an undefined slope. Undefined slope only occurs when I have a vertical line. This means a vertical line. So let's go back to the graph and show you what it means, or just give you a visual. We just did y is equal to 1/2, double equal sign. Right? And then my statement was that if you want to be perpendicular to that, you have to be vertical. The only way to have a vertical line is to write an equation where y is missing. So there's y is equal to 1/2. Here's x is 1. This one has a slope that's undefined. The reason the slope is undefined is if you pick any 2 points on this line and you find the slope, you'll cause division by 0. So that's why a vertical line has a slope that is undefined. A silly way to remember it is a horizontal line. Think of it as skiing on you're skiing on, it's not even a bunny slope, it has no slope at all, you're gonna go nowhere. But if you ski down that vertical line, if you come off of a cliff like that and try to ski down it, you will be undefined when you get to the bottom. It's dumb and silly, but it works. It's kept me on the right side of 0 and undefined for a long time. So those are the cases that you can run into. So you've seen the case where I have a horizontal and vertical. You've seen the case where I have a slope that's an integer. So to find the perpendicular, I end up with the 1 over whatever I had. You've seen an equation where y is not by itself, and you've got to get this into slope-intercept form before you can do anything with it. And then you saw the original here where the slope is 1, so that means my perpendicular one has a -1. All right, so that's the first page of 1.5. Any questions? No? All right. No. All right, so my handwriting is just atrocious in this. So I'm gonna pull up. Yeah, I get that a lot. Yeah. So I'm gonna pull up OneNote just because I know I can write. I can write more legibly in here, and I'm just gonna pull the questions over or just kind of work with them as we go. So these won't match exactly with what you're seeing, but it'll be close. On this page for 1.5, we have 2 lines and 2 types of equations, or 2 equations to use. Let me get my notebook here. I think I just forgot how bad the handwriting can get using a smart notebook. Oh, my mouse has decided to lose its mind. Okay. Oh. I really think this is just a replay of Monday. That's what this is. So there we go. So now we don't have to pretend. Just grab the screen. So I have page 2 of the notes. We have 2 approaches to writing the equations of lines. I have slope-intercept and I have point-slope. For years, I only taught point-slope until students just got so frustrated with it that they couldn't do anything. That the process didn't make any sense, or maybe it's not so much the process didn't make sense, it just kept leading to the wrong answer. So I brought in the point-slope and the slope-intercept form. So I've got 2 questions over here to the left. Write the equation for the line that passes through the points 4, -1, and -2, 7. All right, so I'm going to come down here to the bottom and deal with this a bit more, try to work out what I have. So in order to write the slope-intercept, I need 2 things to be given to me. I need the slope and I need the intercept. That's where it gets its name. Okay. Needed. To get point-slope, all I need is a point and the slope. Okay. Well, right now all I have is 2 points. So that's not gonna, I can't use point-slope and I can't use slope-intercept here. And if you're gonna use the point-slope, those are the things that you're gonna fill in, the point x1, y1, and the slope of them. So I need to find the slope of this line to get started. So the slope, change in y over change in x. Remember the second point I run into is the sub 2s. This first point is the sub 1s. So I'm looking at 7 minus negative 1 over negative 2 minus 4. 7 minus negative 1 is 7 plus 1. Negative 2 minus 4 is negative 6. 7 plus 1 is 8. 8 over negative 6 is negative 4/3. Right? Everybody agree? Yes, no, hello? Okay. So, yes, yes, yes. Okay. Yes, okay. Good, so there's my slope. Okay. So I now have the slope. I have 2 points, so I can go find this equation. Problem is I can take this slope and either one of these points, plug it into point slope, and let me show you what happens. I'm just going to pick the first one, the first point and the slope. Let's plug everything in that we need. Y minus negative 1 is equal to negative 4/3 times x minus 4. And remember that the slope I have found is negative 4/3, and the point that I'm going to use is 4 negative 1. The negative 4/3 comes from the calculation right there. The point comes from, it's either one of the points they gave me to start with. So solve this for y, and you're going to get this in slope-intercept form. Y minus negative 1 is y plus 1. Distribute on the right that negative 4/3. So that's negative 4/3 x. Negative 4/3 times 4 is negative 16/3, minus negative 16 becomes plus 16/3. And here's where this method kind of falls apart for me, or frustrates students, is I need to get y by itself. So I need to subtract both sides by 1. That 1 is similar to this 16/3. It's just doesn't have the same denominator. So I've got 16/3 minus 1, which is what? Well, 1 is, I need the same denominator. 1 is 3/3. Right, and now I have the same denominator, so I can subtract this. This leaves me with 13/3. Right, so there's the equation of the line that passes through 4, negative 1, and negative 2, 7. All right, now let's do that same problem, but use the slope-intercept. So I have the slope, but I still need the intercept. So I'm going to go set off and find b. So I take a point that I'm given and the slope, I plug it in, and then I'll have b left over. I'll solve for that. So same problem. I'm using the point 4, negative 1 and the slope negative 4/3. So negative 1 is equal to negative 4/3 times 4 plus b. Negative 1 is equal to negative 4/3 times 4, negative 16/3 plus b. Add 16/3 to both sides, and this is absolutely a place where the calculator would be used. 16/3, or negative 1 plus 16/3 is 13/3. So now I have my y-intercept. I know the slope to be negative 4/3. So I write the equation. Y is equal to negative 4/3 x plus 13/3. Okay. Both of these are valid. Both of them lead to the correct answer. So consider that as you want to do these problems. Point slope. Once you have a point in the slope, you can find the equation, no problem. Slope intercept. Once you have a point in the slope, you still need to find the intercept. So it's going to cause, so that one needs a little bit more, but I think typically students like using just point slope, find b, and then come back and plug it in. That tends to be their favorite. But whichever one makes you get the right answer, as always, is the one that I want you to do. Okay. So for the next problem, which is not going to fit in the table, I've got write an equation for the line parallel to 2x plus 3y equals 7 and has a y-intercept of, I don't like this notation, and it's because this problem came from the book that I left it this way. I wanted to draw attention to it. It says a y-intercept of 3. That is not correct, okay? Unless the problem tells you that's how we're dealing with y-intercepts, okay? This is not the y-intercept. This is b, okay? So I've got a y-intercept of 3, which really corresponds to the point 0, 3. Now, 3 is the value of b that goes into my equation. So I'm parallel to 2x plus 3y equals 7. So if I'm parallel to that, I must have what, either the same slope or the opposite reciprocal. Which one? Am I parallel? If I'm parallel to a line, how is the slope of the line I'm interested in related to the line? Is it the same? Is it the opposite reciprocal? Yes, the same slope. Good. So I must find the slope of this line. So let's go find it. So everything with a y to one side, everything without to the other. 2x minus 2x is 0. 3y is equal to 7 minus 2x, the same thing as negative 2x plus 7. I would love for y to be by itself because I'm doing my best to solve for it. Okay, so what does that leave me with? Y is equal to, that's negative 2/3 x plus 7/3. Here is that mistake that can happen again. A lot of people will get there and they'll say, and I'm done. You're not. The slope of this line, we did all of that work to find the slope. Okay. All of that work was to find the slope because I'm only interested in that line because it has the slope of the line I'm looking at. So I have a slope of 2, 3, and from the problem, we know that b is equal to 3. So y is equal to mx plus b. I don't have to find b because I've encountered a special situation. And that situation is the point that they gave us is the y-intercept. All right, they told us that the y-intercept is 0, 3. So that's why I get to, whenever that happens, I just get to plug that number directly in for b and I'm done. If I did this with point slope, I would still need to get the same, the process would be the same because I still need the slope. So I know that the slope is 2/3, and I know the point that I'm using is 0, 3. So plug everything in. Y minus y sub 1 equals m times x minus x sub 1. Y minus 3 is equal to negative 2/3 times x minus 0. Y minus 3 is equal to negative 2/3 times x is negative 2/3 x. Negative 2/3 times 0 is 0. Add 3 to both sides. I have y is equal to negative 2/3 x plus 3. There we go. So it leads us to the same answer. Whenever you're given the y-intercept in the problem, by all means take advantage of it. Just understand that point slope works with any point and any slope. Slope intercept works with a slope, but you have to go find that intercept yourself. You've got to go get that b value. Yeah, you could. Yeah, just add that plus 3 on the end. All right, so that's page 2. Any questions? Everybody's agreeing, coming along, no problems? I'm going to leave, there's a question at the bottom that asks you to find the slope, write the equation of the line passing through the point -8, -4, and perpendicular to the line. Y is equal to -1/6x plus 3. Let's see, will you ever have to answer any questions other than that? You could, like in this question, the final answer is still going to be a linear equation. So the answer is always going to end up in y equals mx plus b if the question asks you specifically for the equation of a line. If it asks you for just the slope or just the y-intercept, then yeah, sometimes the answer is just going to be a number or a point. Okay, so I'm going to leave this one for you to do, and I'll I can add a short video right there to skill 4. Let me just put that in my notes to do, because I'm trying to get better about making videos. So skill practice 4. Give that one a shot on your own as well, and then come back and watch the video once I post it, and then see how you did. So next part of this question, next part of this section is correlation. You've heard the phrase correlation and causation. Correlation does not prove causation, or doesn't mean causation is occurring. Whenever I have a data set, if my points are relatively close to each other and they follow the pattern of a line, have a linear pattern to them, so you can see the green dots there. As they are kind of moving from left to right, the points are getting higher. Right? I don't have a bunch of points scattered everywhere. These seem to have some kind of a pattern to it. So the closer those points fall to a straight line, the closer R, which is our correlation coefficient, is to 1. Okay? If my slope is positive, if I'm rising from left to right, R is going to be closer to 1. If I'm falling from left to right, but I still have that pattern, you see how that in the red dots, you see how I'm still falling from left to right, but it's pretty consistently falling, that would be a correlation of -1. So the correlation coefficient is R. The closer it is to 1, the stronger the positive correlation is. So this is positive correlation, and then the next one is negative correlation. Okay. And then this is none. None or little. Okay, so if I've got positive correlation, my points are going to fall close to a line rising from left to right. If my points are falling from left to right, I have negative correlation. And the correlation coefficient is all about how close these fall to a straight line. Not that they're all moving in that direction, but if I draw a straight line, how close are all the points to falling on the line? If all my points fall on a straight line, then I'll have a correlation. If I'm rising from left to right, I'll have a correlation of 1. If I'm falling, I'll have a correlation of -1. And then if I don't have any correlation, as in with this example, nothing really seems to be following a pattern, right? As I move from left to right, I have some points above, some points below, really no pattern there. All right, so for us, I have a data set. I'm going to steal to my next page. And it shows age and systolic blood pressure for a sample of 12 randomly selected healthy adults. Okay. So for this section, what we're going to do is instead of, well, the way we're going to start this is we're going to model this by taking 2 points out of that data set, creating a linear model. So if I get 2 points, I can draw a straight line through them. And picking those 2 points, the problem does it for us. The points are 21, 118, and 51, 130. I'm asked to write a linear model relating y as a function of x, interpret the meaning of that model, and then use that model to estimate the systolic blood pressure for a 55-year-old. All right, so let's first tackle the first question. All right, it's an application problem, but you can pull, we can pretend it's not, because that's really what we do. X is the age in years, Y is the systolic blood pressure in millimeters of mercury. So in order to write the equation of the line passing through these 2 points, I need a point and I need the slope. I have points, I don't have a slope though. So the slope is what? Y2 is 130, Y1 is 118, X2 is 51, X1 is 21. 130 minus 118 is 12. 51 minus 31 is 30. Those are both even, so I can take that to 6 over 15, which I can then reduce to. No, they're both divisible by 3. So 6 becomes a 2, 15 becomes a 5. Okay, so I got a slope of 2/5. What does that mean? What does the slope of 2/5 mean for this problem? Slope of 2/5 means up to fifths per year. Almost. It's really close. And yeah, per year you could do it that way. So we've got 2 over 5. So I'm going up 2/5 of 1 millimeter of mercury per year. But I like to think of it, let me show you what I'm thinking. The numerator is the systolic blood pressure. So this means an increase of 2 points in systolic blood pressure for every 5 years that pass. Does that make sense? The numerator is the age. The numerator is the systolic blood pressure. The denominator is the age. So that 2 is in the numerator. Those are my systolic blood pressure. The denominator is the years that pass. You can do 2 divided by 5 and end up with a slope of 4/10. And that would mean an increase in 0.4 points in systolic blood pressure for every year that passes. Okay. Both of those are valid, but there's the interpretation. I'm going up 2 points in systolic for every 5 years that pass, or I'm going up 2/5 of a point or 0.4 of a point every year. So as we age, our blood pressure tends to go up. Now, part C, that was part B. Part C says use the model to estimate the systolic blood pressure for a 55-year-old round to the nearest whole unit. Right? Well, I have the slope, and I have 2 points given to me. Those 2 points are 21,118 and 51,130. Well, I don't have a linear model yet. And it sounds so scientific. It's like, oh, we're going to bring up, slide rules and protractors and doing stuff. Linear model just, it means find the equation of the line that they gave us. Well, they told us that the line passes through the points 21,118 and 51,130. And then we found that the slope is 2/5. All right, so I'm going to find the linear equation that passes through these 2 points with the slope of 2/5. So I'm going to use slope intercept here and find B. Since they didn't give us an intercept, I've got to go find B. So I'm going to use the first one. Y is 118, slope is 2/5, X is 21, 118, 21 times 2 is 42 over 5 plus B. Going to subtract 42 over 5 from both sides. If you want to know the math that takes place over there, 118 over 1 becomes, where's my number? 118 over 1 becomes 590 over 5. So this ends up being 590 minus 42 over 5. Which is 548 over 5, which is equal to 109.6. So there's my B value, and I know my slope. So the equation of the line, y is equal to, the slope is 2/5. The B value is 109.6. All right. Again, the fraction. So that's a great question, Andrew. Wouldn't you leave this as a fraction? Typically you would, and the problem, but the problem has answers, or has points where the y value is an integer, and the problem tells us, because I read ahead a little bit, use the model to estimate, round to the nearest whole unit. So since we're going to be rounding anyway, we might as well give it, let it be that decimal. And it turns out 590 minus 42 over 5, that is the actual decimal answer. That is 0.6 and it stops. So 109.6 and 548 over 5 are the same thing. They actually are the exact same number. All right. So there's my linear model using the 2 points they gave me. I found the slope, I've got this, and then they've asked us to find it, find y for a 55-year-old man. Okay, well that means what? That means, Y is, we have it right here, 2/5 times, X is the age in years, so that's 55. 55 divided by 5 is 11. 2 times 11 is 22. 22 plus 109 is 131.6. Okay. So that means what? That means a 55-year-old man should have a systolic blood pressure of 131.6, and these are millimeters of mercury. Does it mean that all 55-year-old men will have this blood pressure? Absolutely not. It does not mean that, but it means my model predicts that, and maybe even change the wording so to kind of qualify it at the beginning. Based on the model we have, that's probably an even better answer, right? As opposed to saying this is definitely going to happen. This is a much better way to say it. Because if I picked, notice when I did the problem, picked 2 points in the data set for me. And since it picked those 2 points for me, this line's been created. If I picked any 2 other points, I would end up with a different answer here because my equation would be different. When I do 0.4x plus 109.6, do you mean instead of finding B? The 2/5 is 0.4. 0.4 times 5 is 22. It's the same thing. Yeah, instead of having 2/5, that would be fine. Yeah, you're right. I am inconsistent. I have the slope as a fraction and the y-intercept as a decimal. So I could, if I were consistent, I would have 0.4x plus 109.6. Yeah. So the speeding up the process, that is a good question, but the problem tells us to, part C says to round to the nearest whole unit. That's only in the example of a 55-year-old man. So I would round Y to 132 millimeters mercury if I'm following the directions. So 131.6 would become 132. But I can't round, or I try my best not to round whenever in the steps along the way. Like I don't want to round 109.6 to 110 or anything like that. All right. Okay. So the next page is a data set. And the question asks us to look at this on Desmos. I've already plugged these numbers into Desmos. So we can look at those. This one's not too bad of a problem. And then the last one has us do the same thing as the problem we just did. And then it asks us to use, so this is just the same question that we just saw, write a model for these 2 points, interpret the meaning of the slope, interpret the meaning of the y-intercept, and then predict. So this question is the only one that has new information for us. And the reason it has new information is it tells us to take a look at Desmos and look at the equation that it gives you. So on the left-hand side, you see all the points that are in that page. On the right-hand side, you see all the points. Those are listed. I've moved the X and Y mins and maxes around so all the points are graphed. And then here at the bottom, so to get a table into Desmos, you do the plus sign, and then you tell it a table. You put your X1s and your Y1s, and then you type in this exact phrase. Yes, yes you do. All right, so type in this exact thing. The Y1 is the name of this list. X1 is the name of the variable. You'll end up with your M and your B. That's your slope, that's your intercept. Plug those numbers in and you have a linear equation. That is the best approximation, but instead of using just 2 points to get my line, this process uses all of the points. So we'll pick up here and talk more about this, and then we'll dive into 1.6 and transformations on Thursday. All right. I have no idea how it'll work there, Andrew. That's something y'all have to test. All right. So everybody else good? Any other questions? So 1.5 is due Thursday. You should be able to do all of 1.5, yeah. Yeah, so go ahead and knock it out. All right, stop the recording. There we go. All right, so last time we got into 1.5, I tried to use Smart Notebook with my tablets here, and my handwriting was horrible. So we swapped it out. I lost a bit of time. And so I kind of swapped it out and brought back the OneNote. I don't love the OneNote because when I print or when I submit, make the notes into PDFs, that's when you'll see these weird, like the page will just cut off in the middle of something. So it's not perfect, but it'll work for us. And so I'm gonna make it a point to always use this because it's the only way my handwriting is readable. And so the last thing we did, we grabbed the question off of the last page of the PDFs, got 2 points, created a linear model, defined the slope, defined the intercept, and then discussed what does it mean, what is the Y value, what is the estimated systolic blood pressure for someone 55 years old. I mentioned quickly in passing this page, which is page 3 of the old one of the notes that you have, which has on-base percentages and runs scored for teams in baseball. This is obviously not this year's data, this is from the textbook. And they've got them paired up, on-base percentage and runs scored. So what I'm asking you to do in this is look at the scatter plot on Desmos. So what you're going to do in Desmos is this. You're going to take, I'm going to hide this line really quick so you don't see it. So if you plot all of those points, you're going to go up here to the plus sign, you're going to hit table. Table's going to pop out X1, Y1. All the X1s here, all the Y1s here. Make sure you pair them up, as you know. And then the problem is if you type them all in, but you do something silly like me and use the standard window, you're going to find out that none of this shows up. There's nothing on this graph. Okay, I graphed all those points, I've put all those points on there, and now there is nothing there. The reason there's nothing there is because my window doesn't show them. My window needs to accept the lowest X value and the highest X value. My window needs to accept the lowest Y value and the highest Y value. Now, I don't think there's a fancy way to arrange these. So we're just going to run through, find the smallest number. I think it's 31.9. And then find the largest number, 30, I see a 35, a 34 in there, 34. Yeah, 30, so 31 to 34. And then for the y values, the lowest, there's a 600 something here. And then there's an 834 here. So 691 to 834. So in Desmos, I use the little bar up here on a calculator. You would use the Xmin, Xmax stuff. Lowest y value I need to represent is 30. The highest was 34, so I can do 30 to 35. If I stop there, I still don't have any dots, still don't have no scatter plot because I haven't moved the y yet. So the y values, the lowest was 691, so I'll go down to 650, and then the highest, 849 is the highest. So if I change the window to no, you will not need a graphing calculator for the test. Y-axis 650 to 850. And there are all of our points. You can, on Desmos, you can grab and drag, but here's our scatter plots, okay? So we're asked to take a look at this scatter plot. Yes, Desmos is going to have to be available. So, but we'll work on that. We're going to figure all that out when the test comes around. So yeah, if either you're going to have access to Desmos or I'm not going to give you test questions where you have to do all this. Okay. And probably I'm not going to give you test questions that require the use of this. But yeah, if I do give you a test question and it is required, then yeah, you'll have access to it. All right. So does it look like, do you see any pattern here? Okay. Do the data appear to be rising from left to right, falling from left to right, staying steady from left to right, or maybe they don't have any relationship left to right? It's not super strong, but we can see that my data seems to, as x increases, y increases. And remember, what are these values? X1 is the on-base percentage, y is the runs scored. So it would seem that our graph is saying the more often we're on base, the higher our on-base percentage is, the higher the total runs scored for the team. That makes sense, right? So there's the plot. Second part of the question. Whew, I want that to get out. Second part of the question, write our own linear model. So to do our own linear model, we're going to pick 2 points, find the slope, and then write the linear equation based on that. So I can pick any 2 points I want, and but except for the first two, because they both have the same x value. So if I pick those 2 points, x values are identical, that means I'm going to have a vertical line. So I need to pick something that has different x values. Desmos does give it to you, but that's the linear model from Desmos. Okay, so we're going to make our own, and then we're going to look at the linear model that takes into account all of the data. All right, so let's look at Florida and Milwaukee. All right, so the 2 points, and this is how the problem has been done. This is how we've done every one of the problems so far. We create our own linear model by taking 2 points, 32.7, 730. We find the slope of the line, change in y over change in x. 730 minus 758 over 32.7 minus 33.1 730 minus 758 is negative 28. 32.7 minus 33.1 is negative 0.4. And 28 divided by 4/10 is 70. Okay, and negative divided by negative is a positive. So there's the slope. What does this mean? Okay, a slope of 70. Okay, what's my y values? These are runs, right? What is my denominator? Well, this 70 is written as, it's an integer, so I can rewrite it as itself over 1. What was the units for the denominator? That's the on-base percentage, the OBP. So it looks like for every increase of 1 point in the on-base percentage, a team has an increase of 70 runs scored in the season. Okay, that seems like a lot, but remember, on-base percentage, look at it, it's everything in here is between 31 and 34, or 31 and 35. So just going from 30 on-base percentage of 30 to 31 or 31 to 32, that's going to increase your number of runs by 70. That's amazing. All right, so if that is my slope and I have these 2 points, I need to write the linear equation that represents this line. That is y equals mx plus b. To write the equation, I need the slope and I need the y-intercept. I was not given the y-intercept, so I'm going to have to go find that. I'm going to find b, and I'm going to use just the first point that I run into, 33.1758, and a slope of 70. So y is equal to, whoops, y is gone because y is 758. Slope is 70. X is 33.1 plus b. 70, and I'm going to do this all in one step. 758 minus 70 times 33.1 gives me a b of negative 1,559. All right, so what's my equation look like? There's b, there's m. So the equation that I have found, the linear model I have created, is y is equal to 70x minus 1,559. Now, let's talk about what this means, because this is a pretty big deal. Okay, so if you can correctly identify what this means for the problem, this is going to go a long way to explaining how this works. Okay. I was talking to a student in my office the other day, and the key part or the key point in algebra is that there are only when we go to describe something that occurs in the real world, we can find functions and equations and graphs that match for some period of time, but we're never really going to find one that just gets it dead on. Okay, and take a look at this example first. I have 70x minus 1,559. That negative 1,559 would correspond to if I had 0 runs, which is x. If my on-base percentage was 0, then my runs scored would be negative 1,559. Is that possible? Absolutely not. Right? If I don't have any on-base percentage, if no one ever gets on base, I would score 0 runs, maybe some home runs, some single, some 1-run home runs, but that would actually count for on-base percentage too. So no, it would just be 0. So this line is useful for us, but it's only useful in this in my data set over here in the values around x is 30 to 35. It doesn't do me any good when on base, if I go for x greater than 100, because you can't have an on base percentage greater than 100, and it wouldn't do me any good for negative x because it doesn't make any sense. I can't have on base percentages negative, and it also doesn't make a lot of sense for me really until the runs scored comes back positive. Does that make sense? Does that concept, that idea make sense? This is a linear model, and if I want to use it, and again, I'm getting it from picking 2 points in my graph. If I want to use it to predict what's the on-base percentage if, what's the number of runs scored if on-base percentage is 35. So that means x is 35. So I'm looking at y is equal to 70 times 35 minus 1,559. Okay, 35, we don't have any values over here on the table that are all the way up to 35. I think we have 34.8. So we are expecting a number that's in the, it's in or around the numbers in the table, but it's going to be better. 70 times 35 minus 1559 is 891. So this means if the on-base percentage is, if the on-base percentage is 35, estimated number of runs is 891. Okay. That's way up there, isn't it? Okay. Does it fit within our data? Does it make sense? There's a point, 34.8. We see one coming out to 820. I have another 800 here, 34.7. I have an 865. The problem is, though, when I created this linear model, the 2 points that are the closest to this example aren't included. The only 2 data values I took into account are the totals from Florida and the totals from Milwaukee. So all of this data is based on 2 data points. What I would love to do is find the line of best fit if I use all of the points. Okay, now that does not mean find the slope of every line, every pair of every lines. Okay, what it does, and I'm going to show you this in Desmos. I don't want you to think too much about this, but we're going to get a calculation of linear regression. Okay, and it's going to look like this. In Desmos, you have to type this exact phrase in. So y sub 1, you get downstairs by typing the underscore, that's shift, and the dash beside 0. Then there's a tilde right here. There's the slope m, x sub 1 plus b. Okay, so here is what I'm getting from Desmos. And then let's convert that or show you what that looks like. Okay, so Desmos spits back these numbers. If y sub 1 is equivalent to, or what I'm looking for is the linear model. And I have 2 numbers here. I have my slope, my parameters, and my y-intercept. That's it. I just need those. They gave me the format. This is a linear equation, so I'm just going to plug these numbers. I'm going to plug them in up here. And I'm going to find my Desmos model says that the linear equation or the linear model should be y is equal to 49.2x plus negative 870, which is minus 870.94. Okay. Yes, we will go on to higher order problems in Desmos. So let's compare our model, where we had 891 runs, to this model. If x is 35, y is equal to massive difference, right? In both values. The slope is much more shallow, and the y-intercept is larger, right? Instead of being negative 1,559, it's just negative 870. Plug all that in, times 35 minus 87094, and we find y is 851.06. So then for this model, if x is 35, y is approximately 851. I'm rounding it just because they're runs. They don't make a whole bunch of sense as decimal, but 850.06 is fine here too. And this is the OBP on base percentage, and then these are the runs. All right, which one of those is a better estimate, you think? Do you think the problem above is, or the problem on the one on the bottom is? Which one of these falls more in line with the data that we can see? Right. So let me show you where these are on the graph and then see if you can answer that question. If I list 35,851, you see it pop up over here? There it is, right there. That seems to fit along with our data. This is the point we get by following the slope or following the equation given to us by the Desmos linear regression. The other point was 35,891. Oh, that's in the wrong place. That's not even on the map. I'm gonna have to zoom out to get it. There it is. Okay. It's quite an outlier for us, right? It's way out there. So why is this one better? Why is this 851 better than the 891? Because it's more in line with what we have. That's the highest on base percentage that we see, but my runs are not so much larger than all the other values that they don't seem right. And the reason for that is this linear regression, what it does is it takes every point in here and it draws a line. And it's also called the line of least squares. And what that means is you get a line, and I'm going to show you. Here's the line. This is the other part. It graphs. What this does mathematically is it takes every point that is on the graph. It finds the distance between the point and the line, and then it creates a square where the top left touches the point, the bottom right touches the line, or if I'm down here, the top left touches the line, the bottom right touches the point. What it does is it goes through and finds what is the way to make the area of all of those squares the smallest number possible. So you're literally looking at this line is the equation. These are the set of points that are the least distance away from every point in the data set on average. So that's what this is doing. Okay, so this is as good as it gets. What about our line that we made up? For our linear model, we had 70x minus 1559. There's our model. Okay. You can see in that purple one, you can see how we're not getting that same benefit, right? This line is much farther away from this point or this point. It seems to be a lot closer. All the points above it are much closer to it, and the points below it seem to be far away. But look at what it does. It's hitting these 2 points because those are the 2 points we use to create the line. If I had picked a different point, I would have a different line. I could have a line passing through these two. So all is to say, the linear regression takes into account every single point and draws a line based on all of the data you have. The linear model we created only took into account 2 data points. So whenever I get a chance to use linear regression, I do. And because it's just better, because it considers every single point instead of just the 2 points that I need to draw a straight line. All right, so that's 1.5. Any other questions on that? Okay. All right, then let's go to 1.6 and let's start talking about transformations.